In this lesson we are going to see the definition of probability. We are going to see first of all the classical definition, then the axiomatic definition, and some examples. As there are many ways of defining a probability, here we are going to see the main two ones. We are going to see the problems that we have when we derive the probability in the classical way, and then we are going to see the axiomatic definition. We start by giving an example for the classical definition. So we have the following experiment. We have an urn that contains balls, and we are going to want to find what is the probability of drawing a red ball. We see that we have two red ones, two green ones, a white and a grey one. According to the classical definition, the probability that we draw a red ball would be 2 out of a total number of 6 balls. So the probability of the red ball is the number of red balls divided by the total number of balls in the urn. For this classical definition, in general, if we have any event, the probability of this event would be defined as the number of elements in the event A divided by the total number of elements in S. Of course, in order to use this probability, to use this definition, we are talking about equally likely outcomes. We are talking about, like in the example we've seen, every ball to have equal probability of being picked. So actually, trying to define what the probability is, we have already used the notion of probability. When we talk about equally likely outcomes, we mean that the outcomes have equal probability of being picked. So you can see here that although we try to give a definition of the probability, we actually have already used the notion of probability. And that's the problem with this definition. So we are going to see another definition now, the axiomatic definition, which does not have this problem. We have S, as we have saying, we denote the sample space, and an event A from this sample space, and we assign a number which we denote by P of A. This number will be called probability of A when it satisfies some axioms. First of all, it satisfies the axiom that the probability of any event from the sample space should be greater or equal than 0. It cannot be a negative number. And also, the probability of the sample space S should be 1. We have defined that we start by saying that having made clear what the sample space is, the probability of that sample space should be 1. Also, another property is if we take a sequence of mutually exclusive events, A1, A2, A3, and so on. I remind you here that mutually exclusive, we mean that if they taken in pairs, their intersection doesn't have any common elements. So A1 with A2 taken, they do not have any common elements. A2 with A3, A1 with A3, and so on. Then the probability of the union of these events will be equal to the sum of their probabilities of each event. I am going to write now clearly mathematically what do we mean using these symbols. We have that the union of the events AI, the infinite union, is A1 union A2 union A3, and so on. The sum from I to 1, from I1 to infinite of the probability of AI is the probability of A1 plus the probability of A2 plus the probability of A3, and so on. So use this symbol in mathematics to denote the summation. Now we are going to see graphically the third property using Venn diagrams. Note here that this property is for the union of an infinite number of events, but using Venn diagrams, we are going to have only a finite number of events. The property we have seen holds for finite number of events, but we are going to prove it later on. So we have event A, event B, and event C. They are mutually exclusive events. They do not have, if taken in pairs, any common elements. A and B have no common elements, A and C, and B and C. So the probability of A union B union C is equal to the probability of A plus the probability of B plus the probability of C. We are going to see later that if the events are not mutually exclusive, this formula is not true. So, some more rules that we are going to prove now, we are going to see for probability. First of all, the probability of the empty set is 0. We are going to show this property using some simple mathematics. So, we know that the empty set has no elements. So, if we take the empty set intersection with itself, we are going to have again the empty set, as there are no elements in here. So using the third property, we have that the probability of the empty set union empty set, union, and so on will be taken to every time they have no common elements. So we can write that this is equal to the probability of the empty set plus probability of empty set plus and so on. Now this union, the union of empty sets, we know that it is actually this one, the empty set. No matter how many times we take the union of the empty set, we are going to have again the empty set. That will be equal to the probability of the empty set. Looking here, this equality, I'm going to write it again clearly. We see that in order for this to be true, we have to have that the probability of the empty set is 0. This holds only in the case that these are 0. We cannot add the same number other than 0 infinite times and get the same number again. So it has to be 0. Now we are going to see how we can prove the third property in the case when we have finite elements, finite number of events. I'm going to write again the third property so we can look at it. When there are infinite number of events, we know that this holds. Now, if we take the union of these events, which we said would be A1, I2, let's say AN plus 1, and so on, and we assume that all the events from here are the empty set, so each one of these is actually the empty set. Their union will be the empty set as well. We have that the probability of the union of the infinite events is actually the probability of the union of the finite ones. Looking here, we see that all these are the empty set and can't be left out. So, according to this will be equal to the sum, the infinite summation of the probabilities. So it is actually the probability of A1 plus probability of A2 plus probability of AN plus all other probabilities. Now we know that the probability of a n plus 1 and all other probabilities after a n 1 would be 0, as this is the empty set. So we have proved before the probability of an of the empty set is 0. And so this will become the probability of a1 plus the probability of a2 plus the probability of an. It will be the finite summation, as we write in maths, of the probabilities of the events ai from I starts from 1 up to n. Another property for probabilities is that the probability of the complement of the event A is equal to 1 minus the probability of A. Let's prove this as well. We know that the union complement A is our sample space, and A intersection its complement is the empty set. We know that A has no common elements with its complement. So the probability of S, according to the property we've proved before, we showed that the probability of union of finite events is equal to the sum of the probability of each event. So here we have that the probability of S will be the probability of A or its complement, which is equal to the probability of A plus the probability of the complement of A. We can do this as we know that A and the complement of A have no elements in common. They're mutually exclusive. From here, we know from the first property that the probability of the sample space is 1. And so this is equal to the probability of A plus the probability of the complement of A. Reordering this equation, we can now get that the probability of A equals to 1 minus the probability of the complement of A, or the probability of the complement of A is 1 minus the probability of A. So when we want to calculate probabilities of a complement of an event, we are going to take this equation to use this property. Also, another property is that, in general, when A and B are two events that they do not have to be mutually exclusive, the probability of their union is the probability of A plus the probability of B minus the probability of their intersection. Let's see how we can prove this. The union of A and B is A union the B minus A. We are doing this because when we are proving properties like that, or in examples, we try to write unions as unions of mutually exclusive events. We have seen that in that case we can use the property of the probability that the probability of their union is equal to the summation of the probability of each event. And so it's much easier when we do calculations. So when we have to prove properties like this or work with examples like this, we do this trick. We always try to write unions of events as unions of mutually exclusive events. That's what we have done here. We have written A union B as A union B minus A. So from here, we know now that the probability of A union B is the probability of A plus the probability of B minus A. We can do that. We can add up the probabilities of these two, as we know that A and B minus A do not have any common elements. A intersection B minus A is the empty set. Also, we can write A union B as B union A minus B. Thinking the same way as before, that B and A minus B do not have any elements in common, we can write that the probability of A union B is the probability of B plus the probability of A minus B. Also, A minus B and B minus A are mutually exclusive events. That is, A minus B intersection B minus A is the empty set. A intersection B is also mutually exclusive with A minus B and with B minus A. So we have that A minus B union B minus A union A intersection B is A or B. We see that we have the part of A here that doesn't include B, the part of B here that doesn't include A, and the remaining, the common part of A and B here. As they are mutually exclusive events, we can write the probability of A minus B union B minus A union A intersection B is equal to the probability of A union B. And now we can say that the probability of A minus B plus the probability of B minus A plus the probability of A intersection B equals to the probability of A or B. I remind you that we have also derived from before. I rewrite here that A union B is the probability of A plus the probability of B minus A, and the probability of A union B is also the probability of B plus the probability of A minus B. If we add up this together, we have that 2 times the probability of A union B is the probability of A plus the probability of B plus the probability of B minus A plus the probability of A minus B. We see here that this part plus this part is here, and so this would be equal to that minus that, would be equal to the probability of A union B minus the probability of A intersection B. So we have that 2 times the probability of A union B is probability of A plus the probability of B plus the probability of A union B minus the probability of A intersection B. We can see that we have 2 times this here, 1 time this here. We can cancel out 1 with 1 here. If we bring it this side of the equation, we'll have A union B equals the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. This property is one that we are going to use a lot because most of the events we are going to see are not mutually exclusive. So we are going to use this property in order to calculate probabilities of their union. Finally, we have that if A is a subset of B, then the probability of B minus A will be equal to the probability of B minus the probability of A. This is an easy one to prove. We have that. As before, we are going to write A and B as a union. We are going to write B as a union of disjoint events. We are going to write B as A union B minus A. So now we can use the property that probability of B will be probability of A plus the probability of B minus A. And so from here, the probability of B minus A is the probability of B minus the probability of A. Now that we have proved mathematically these properties, we are going to see how we can going to show them using Venn diagrams. Venn diagrams are an easy way to understand the properties, but they are not a way to prove a property. This is done as it has been shown mathematically. We have the sample space S, we have an event A, we have an event B, their intersection is not the empty set, it's this common part here, and we can see that what we have proved before, that the probability of A or B, the probability of A union B, is the probability of A of this part plus the probability of B. We saw that if we add up the probability of this and the probability of this, we actually is like putting this, taking into consideration this twice. So we have to take this part out once. So it's the probability of this plus the probability of this minus the probability of their intersection. Another rule is that if S is a sample space of an experiment and has n points that are equally likely to occur, now we can talk about equally likely events to occur because we have defined probability, then for any event A of S, the probability of A equals with the number of elements in A divided by the number of elements of S. Now that we have defined probability properly, we're going to see some examples. Let's take the example of the two dice. We throw two dice, a green one and a red one, and the sample space and the possible outcomes can be shown in this table. We can remember that these are pairs, so if the green die brings a 3 and the red one a 4, we have the pair 3, 4. Now, if we're interested in the event at least 1, 6, we are interested in these outcomes, these highlighted light blue elements of the table. Now, let's say that we are interested in the probability of A. According to the rule we have seen before, the probability of A will be the number of elements in the event divided by the total number of elements in the sample space. So A has 11 elements. We can see here 6 and 5, 11 elements divided by the 36 total number of elements in the sample space. So the probability of A, it's 11 divided by 36. Now, if we want to calculate the probability of the complement of A, that means that we are not going to observe any 6. So we actually talk about these elements in the sample space, the ones that do not include any 6. We have the probability of its complement is, using the rule we have proved, 1 minus the probability of A, which is 1 minus 11 over 36. It's 25 over 36. In any way, this could be found if we count the elements of the complement. We see that we have 25 elements here, 36 in total, so we have 25 over 36. In this case, both ways to calculate the complement, the probability of the complement of A are easy, but in more complicated examples, we are going to see that using the rule, it's much easier than calculating the probability of its own. In the example of the two dice, if we have the event B a red 6 and the event C a green 6, shown here highlighted the blue color for the green 6 and the yellow color for the red 6, we see that they have only one element in common, element 6, 6. Also, the probability of their union will be the probability of B plus the probability of C minus the probability of A the probability of B intersection C. We calculate this. The probability of B is 6 over 36 plus 6 over 36 minus 1 over 36. It's 11 over 36. So we have calculated the probability of union B and C. Another example would be the event the D is a red 6 and D we have a red 6 and a green even. So here we see that E is a subset of D, and so D minus E are the elements 1, 6, 3, 6, 5, 6. We have taken out the elements of E, the 2, 6, the 4, 6, and the 6, 6. And so the probability of D minus E, using the rule we have seen, is the probability of D minus the probability of E, which we calculate is 3 over 36. So what we have seen in this lesson is the definition of probability. First of all, we've seen the classical definition and the problems which there are in the classical definition, the axiomatic definition, and several examples. For more information on this lesson, you can visit the web page of UNINETTUNO MedNetU project.